This meeting is being recorded.
This second video on chapter 1 will focus on the scientific method. So we are still in chapter 1. And so chemists are scientists, and as scientists, they use the scientific method. The scientific method is a process for trying to understand nature by observing nature and the way it behaves, and by conducting experiments to test our ideas. So before we move on to the Khan Academy video, let me give you the key characteristics of the scientific method. First, there is observation of the nature. Second, you formulate an hypothesis to try to explain your observation. Third, you test the hypothesis by conducting experiments. The experiments will lead to results or data that then you can report. That's step 5. And then you can loop again and change or not your hypothesis and do step 2 to 5 repeatedly. But ultimately, if possible, you want to formulate laws or theories. That's the goal of the scientific method, is to arrive at laws and theories.
This meeting is being recorded.
So we'll watch a video from the Khan Academy about the scientific notation.
The scientific method, which at first might seem a little intimidating, but when we walk through it, you'll see that it's actually almost a common sense way of looking at the world and making progress in our understanding of the world and feeling good about that progress of our understanding of the world. So let's just use a tangible example here, and we'll walk through what we could consider the steps of the scientific method. And you'll see different steps articulated in different ways, but they all boil down to the same thing. You observe something about reality, and you say, well, let me try to come up with a reason for why that observation happens, and then you try to test that explanation. It's very important that you come up with explanations that you can test, and then you can see if they're true, and then based on whether they're true, you keep iterating. If it's not true, you try to come up with another explanation. If it is true but it doesn't explain everything, well, once again, you try to explain more of it. So as a tangible example, let's say that you live in I don't know, northern Canada or something, and let's say you live near the beach, but there's also a pond near your house, and you notice that the pond tends to freeze over sooner in the winter than the ocean does. It does that faster, and it even does it at higher temperatures than when the ocean seems to freeze over. So you could view that as your observation. So the first step is you're making an observation. Observation. In our particular case, it's that the pond freezes over at higher temperatures than the ocean does, and it freezes over sooner in the winter. Well, the next question you might want to, or the next step you could view as a scientific method. It doesn't have to be this regimented, but this is a structured way of thinking about it. Is, well, ask yourself a question. Ask a question. Why does... So in this particular question, or in this particular scenario, why does the pond tend to freeze over faster and at higher temperatures than the ocean does? Well, you then try to answer that question. And this is a key part of the scientific method, is what you do in this third step, is that you try to create an explanation. But what's key is that it is a testable explanation. So you create a testable explanation. Testable explanation. And this is kind of the core, one of the core pillars of the scientific method. And this testable explanation is called your hypothesis. Your hypothesis. And so in this particular case, a testable explanation could be that, well, the ocean is made up of salt water, and this pond is fresh water. So your testable explanation could be salt water has lower freezing point, has lower freezing point, lower freezing point. So it takes colder temperatures to freeze it than fresh water, So this right over here, this would be a good hypothesis. It doesn't matter whether the hypothesis is actually true or not. We haven't actually run the experiment, but it's a good one because we can construct an experiment that tests this very well. Now, what would be an example of a bad hypothesis, or something that you couldn't even necessarily consider as part of the scientific method? Well, you could say that there is a fairy that blesses, that, let's say, that performs magic, performs magic on the pond to freeze it faster. Freeze it faster. And the reason why this isn't so good is that this is not so testable, because it's depending on this fairy, and you don't know how to convince the fairy to try to do it again. You haven't seen the fairy, you haven't observed the fairy, it's not based on any observation, and so this one right over here, this would not be a good hypothesis for the scientific method. So we would want to rule that one out. So let's go back to our testable explanation, our hypothesis. Salt water has a lower freezing point than fresh water. Well, the next step would be to make a prediction based on that. And this is the part where we're really designing an experiment. So you could just view all of this as designing, let me do this in a different color, where we want to design an experiment. Design an experiment. And in that experiment, let's say, and let's see, the next two steps I will put as part of this experimental. Whoops, I messed up. I did my undo step. So the next part that I will do is the experiment. Experiment. And there you go. So the first thing is, we'll say there's all sorts of things that are going on outside. The ocean has waves. Maybe there are boats going by that might potentially break up the ice. So I just want to isolate that one variable that I care about, whether something is salt water or not. And I want to control for everything else. So I want to control for whether there's waves or not, or whether there's wind, or any other possible explanation for why the pond freezes over faster. So what I do in a very controlled environment, I take 2 cups. I take 2 cups. That's 1 cup and 2 cups. And I put water in those cups. And let's say I start with distilled water, but then this one stays, the first one right over here stays distilled. And distilled means that through evaporation, I've taken out all of the impurities of that water. And in the second one, I take that distilled water and I throw a bunch of salt in it. So this one is fresh, very fresh. In fact, far fresher than what you would find in a pond. It's distilled water. And then this is over here, this is salt water. So you wouldn't see the salt, but just for our visuals, you depict it. And then we would make a prediction. We'd make a prediction, and we could even view this as step 4, our prediction. We predict that the fresh water will freeze at a higher temperature than the salt water. So what prediction, let's say the fresh freezes at 0 degrees Celsius, but salt doesn't. Salt water doesn't. Salt water doesn't. So what you then do is that you test your prediction. So then you test it. And how would you test it? Well, you could have a very accurate freezer that is exactly at 0 degrees Celsius, and you put both of these cups into it. And you want to make sure that they're identical at everything, where you control for everything else. You control for the surface area. You control for the material of the glass. You control for how much water there is. But then you test it. And then you see what happened from your test. You leave it in overnight. And if you see that the fresh water has frozen over, so it's frozen over, but the salt water hasn't, well, then that seems to validate your testable explanation, that salt water has a lower freezing point than fresh water. And if it didn't freeze, well, it's like, okay, well, then maybe or if there isn't a difference, maybe either both of them didn't freeze or both of them did freeze, then you might say, well, okay, that wasn't a good explanation. I have to find another explanation for why the ocean seems to freeze at a lower temperature. Or you might say, well, that's part of the explanation, but that by itself doesn't explain it. Or you might now want to ask even further questions. Well, when does salt water freeze? And what else is dependent on? Do the waves have an impact? Does the wind have an impact? And so then you can go into the process of iterating and refining. So you would then refine, and iterate on the process. When I'm talking about iterate, you're doing it over again, but then based on the things that you've learned. And so you might come up with a more refined testable explanation, or you might come up with more experiments that could get you a better understanding of the difference between fresh and salt water. Or you might try to come up with experiments for what is it about the salt that makes this water harder to freeze. So that's essentially the essence of the scientific method. And I want to emphasize, this isn't some, bizarre thing. This is logical reasoning. Make a testable explanation for something that you're observing in the world, and then you test it and you see if your explanation seems to hold up based on the data from your test. And then whether or not it holds up, you then keep going and you keep refining and you keep learning more about the world. And the reason why this is better than just saying, oh, well, look, okay, I see the pond has frozen over and the ocean hasn't. It must be the salt water, and I just feel good about that, is that you can't feel good about that. There's a million different reasons, and you shouldn't just go on your gut, because at some point your gut might be right 90% of the time, but that 10% that it's wrong, you're going to be passing on knowledge or assumptions about the world that aren't true, and then other people are going to build on that, and then all of our knowledge is going to be built on kind of a shaky foundation. And so the scientific method ensures that our foundation is strong. And I'll leave you with the gentleman who's often considered to be the father, or one of the fathers, of the scientific method. He lived in Cairo and in what is now Iraq, nearly 1,000 or roughly 1,000 years ago. And he was a famous astronomer and physicist and mathematician. And his quote is a pretty powerful one, because I think it even stands today. The duty of the man who investigates the writings of scientists, if learning the truth is his goal, let me start over just so I get the dramatic effect right. The duty of the man who investigates the writings of scientists, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency. Hassan ibn al-Haytham, and his Latinized name is Al-Hazan. So he's saying be skeptical, and not just skeptical of what other people write and read, but even of yourself. And another aspect of the scientific method, which is super important, is if someone says they made a hypothesis and they tested and they got a result, in order for that to be a good test, and in order for that to be a good hypothesis, that experiment has to be reproducible. Someone can't say, oh, it was only a certain time that only happens once every 100 years, and not that's why it happened that day. It has to be reproducible. And reproducible is key, because then another skeptical scientist like yourself can say, let me see if I can reproduce it. Let me not just believe it because that person looks like they're smart and they said that it is true.
This meeting is being recorded.
Let's look at the key characteristics of the scientific method again. So the first step is observation, which is a way of acquiring information about nature. Some observations are simple descriptions about the characteristics or behavior of nature. For example, if you are asked to observe the soda pop and give your observations on paper, you could write that the soda pop is a liquid with a brown color and a sweet taste. Bubbles are seen floating up through it. This would be classified as a qualitative observation because it contains no number, just words. But observations can also be quantitative observations, because you could look at the nutrition fact on the soda can and observe that 240 milliliter serving of soda pop contains 27 grams of sugar. That's a quantitative observation because there is a measurement, and a measurement compares to a standard numerical scale what you have in your sample. So that's quantitative, and that's what scientists prefer to have, because measurements allow you to move on and go further from observations. Next, you do an hypothesis. An hypothesis are a tentative interpretation or explanation of your observations. And here you could say, well, the sweet taste of soda pop is due to the presence of sugar, for example. So a good hypothesis is one that can be tested to be proven wrong. So this so a good hypothesis is one that you can use to base your experiments, right? You can make an experiment that will test this hypothesis. And one test may invalidate your hypothesis. So next you do experiments, and they should be highly controlled, and they will invalidate or validate your hypothesis. And what it means to be highly controlled, it means typically you will have a control, and then you will repeat the experiment by changing only one variable at a time. This way it's controlled. You can say the effect of changing the variable will be due to that variable only. So can you think of a way to test whether the sweet taste of soda pop is due to the presence of sugar? I think given the example we just saw, we could have a regular soda pop and then ask to have a soda pop where you only remove the or not put or add the sugar, and then drink to taste and see the difference in taste. So this leads to results. Experiments leads to results that will either validate, which means confirm, or invalidate, which means deny your ideas. When your ideas are invalidated, you may have to discard, or usually you need only to modify your hypothesis, because many times experiments invalidate only parts of the hypothesis or theory. So you only need to modify your hypothesis to try to taste it again. But be careful when your experiments and results validate an idea. It's not the proof that your idea will always hold. For example, if you are having a soda pop, a regular soda pop with sugar in it, and then you are testing a diet pop that has, let's say, aspartame or stevia in it, they will both taste sweet, but the sweetness will not be due to the same molecule, right? It will not be necessarily due to sugar, because stevia or aspartame are artificial sweetener that bring no calorie, but that give a sweet taste. So you see that results may not always validate your idea. Next, when you have a large group of observations, you know, when you see pattern in your observations, you can generalize them into a single statement, and we call that a natural law. For example, Antoine Lavoisier, a French chemist, developed the law of conservation of mass, which says, in a chemical reaction, matter is neither created nor destroyed. This law is still valid nowadays. This was established in the, you know, maybe 2 centuries ago. So this is still a valid law. So laws explain things, but they do not describe them. For example, Newton could predict the behavior of a dropped object, but he could not explain why it happened. So laws are good only to predict future observations, because you have seen patterns in some kind of observations, and so you know if you repeat that kind of experiment, you will come up with the same outcome. So that's what laws are allowing you to predict. Ultimately, you want to arrive at a theory. Scientific theory summarizes a group of hypotheses that have been supported with repeated testing. You know, when you keep repeating experiments that are tied to an hypothesis, then that hypothesis gets stronger and stronger, and you can come up with a theory. A theory is valid as long as there is no evidence to dispute it. So therefore, theories can be disproven, but they are held as truth until, an experiment may disprove it. If enough evidence accumulates to support an hypothesis, then the hypothesis can become accepted as a good explanation of a phenomenon. And so one definition of a theory is to say that it's an accepted hypothesis. Let's look at an example of chemical theory. The Dalton's atomic theory. Dalton established his theory in 1808. And it says, or part of it says, that all matter is made of atoms, and atoms are indivisible and indestructible. And so this atomic theory of Dalton is still valid today, and it has been proven correct. But there are some tweaks in it. So, for example, atoms are indivisible and indestructible is not held as true, but all matter is made of atom is still held as true. So it has been modified by other scientists afterwards, given what the experiments allowed us to see. And so this theory, the base of it is still true, but it has been tweaked and modified to give a better explanation of the experiments that have followed. So what's the difference between an hypothesis and a theory? An hypothesis is an explanation of a single or a small number of observations. It's really coming from, a single person looking at one thing. But a theory is an explanation that extends beyond individual observations to an understanding of the underlying causes for the way nature is or behaves. So a theory is trying to explain more generally. It's like a model of nature, and so it explains more than just one thing. It can explain many different kinds of observations that are seen. And what's the difference between a law and a theory? One way to tell a law and a theory apart is to ask if the description gives you a means to explain why. If it explains why, then that's a theory, because theories answers the question, why does something happen? Laws are answering the question, what will happen? They are more here to tell you what you will observe, but they are not explaining why it happens. So let's go through another video that will help you even more understand the difference between laws and theories.
Chat with a friend about an established scientific theory, and she might reply, well, that's just a theory. But a conversation about an established scientific law rarely ends with, well, that's just a law. Why is that? What is the difference between a theory and a law? And is one better? Scientific laws and theories have different jobs to do. A scientific law predicts the results of certain initial conditions. It might predict your unborn child's possible hair colors, or how far a baseball travels when launched at a certain angle. In contrast, a theory tries to provide the most logical explanation about why things happen as they do. A theory might invoke dominant and recessive genes to explain how brown-haired parents ended up with a red-headed child, or use gravity to shed light on the parabolic trajectory of a baseball. In simplest terms, a law predicts what happens, while a theory proposes why. A theory will never grow up into a law, though the development of one often triggers progress on the other. In the 17th century, Johannes Kepler theorized cosmic musical harmonies to explain the nature of planetary orbits. He developed 3 brilliant laws of planetary motion while he was studying decades of precise astronomical data in an effort to find support for his theory. While his 3 laws are still in use today, gravity replaced his theory of harmonics to explain the planet's motions. How did Kepler get part of it wrong? Well, we weren't handed a universal instruction manual. Instead, we continually propose, challenge, revise, or even replace our scientific ideas as a work in progress. Laws usually resist change, since they wouldn't have been adopted if they didn't fit the data. Though we occasionally revise laws in the face of new, unexpected information. A theory's acceptance, however, is often gladiatorial. Multiple theories may compete to supply the best explanation of a new scientific discovery. Upon further research, scientists tend to favor the theory that can explain most of the data, though there may still be gaps in our understanding. Scientists also like when a new theory successfully predicts previously unobserved phenomena, like when Dmitri Mendeleev's theory about the periodic table predicted several undiscovered elements. The term scientific theory covers a broad swath. Some theories are new ideas with little experimental evidence that scientists eye with suspicion or even ridicule. Other theories, like those involving the Big Bang, evolution, and climate change, have endured years of experimental confirmation before earning acceptance by the majority of the scientific community. You would need to learn more about a specific explanation before you'd know how well scientists perceive it. The word theory alone doesn't tell you. In full disclosure, the scientific community has bet on the wrong horse before. Alchemy, the geocentric model, spontaneous generation, and the interstellar ether are just a few of many theories discarded in favor of better ones. But even incorrect theories had their value. Discredited alchemy was the birthplace of modern chemistry, and medicine made great strides long before we understood the roles of bacteria and viruses. That said, better theories often lead to exciting new discoveries that were unimaginable under the old way of thinking. Nor should we assume all of our current scientific theories will stand the test of time. A single unexpected result is enough to challenge the status quo. However, vulnerability to some potentially better explanation doesn't weaken a current scientific theory. Instead, it shields science from becoming unchallenged dogma. A good scientific law is a finely tuned machine, accomplishing its task brilliantly, but ignorant of why it works as well as it does. A good scientific theory is a bruised but unbowed fighter who risks defeat if unable to overpower or adapt to the next challenger. Though different, science needs both laws and theories to understand the whole picture. So next time someone comments that it's just a theory, challenge them to go 9 rounds with the champ and see if they can do any better.